Let's continue with chapter 1. Signals can be classified into several classes. I have arranged the classes of signals in pairs. So I will try to explain to you each of these classes of signals. I have also recorded short videos. I hope that those videos will be able to help you in understanding the different classes of signals. And I've also recorded some videos for showing you some examples. Okay, the first one, continuous time signals and discrete time signals. Continuous time signals are those specified for every real value of the independent variable. So in this course, the independent variable is time. So continuous time signals are signals that are specified or which has values of time. Yeah, the independent variable or the time is continuous. It takes any value on the real axis. While discrete time signals are signals that are specified only for discrete values of the independent variable. It is discrete time signals are usually generated by sampling. We sample the continuous time signal to get the discrete time signals. It only has values at equally spaced intervals along the time axis. So in this course, we look at discrete time signals which are equally spaced, which exist at equally spaced time intervals along the time axis. So because we're looking at the time as the independent variable for this course. So here are some examples. So you can see here, okay, when we say continuous time signals, discrete time signals, it is referring to continuous value or discrete values of the time. If we usually plot the independent variable on along the horizontally, so we put the independent variable horizontally, so the x-axis. So for continuous time signals, that means for every values of the horizontal axis, there exists the amplitude values. And for discrete time, only the signal only exists at discrete values of the time, right? So that's the difference between continuous time and discrete time. Okay, the next time is analog and digital. If continuous and discrete, referring to the time or the independent variable or the horizontal axis. Well, now analog and digital is describing the amplitude. Okay, for analog signals, a signal whose amplitude can take on any value in a continuous range. Okay, so now it's the vertical axis. Okay, so the vertical axis, the amplitude exists for continuous range. Can be continuous time and discrete time, meaning that the horizontal axis can be either continuous or discrete. Okay, so for analog signals, the amplitude is continuous, but the horizontal can be continuous or discrete. Now for digital signals, digital signals are signals whose amplitude can take only a finite number of values. A digital signal whose amplitude can take only m different value is said to be M-array or M-array. Binary, okay, binary signals are special cases of where m is equals to two values. So for binary signals, we have values of 0 and 1. Okay, so this examples. So you see here, when we talk about analog or digital signals, we are referring to the amplitude. So analog signals, we have a continuous range of the amplitude, while digital signals, we have values which are the discrete. The amplitude are discrete. Okay. Analog corresponds to a continuous y-axis, while digital corresponds to a discrete y-axis. If we try to, okay, if we, based on what the four signals, the four classes of signals that we've seen so far, Okay, there are two parts there are two things which we need to look at. One is the amplitude, and then the next one is when do the signals exist. So if when we are naming a signal, we first look at the amplitude, then we look at the time. So let's say if, for example, analog continuous time signals. So the first part, analog, refers to the amplitude, and then continuous time, meaning that it exists in continuous time. The horizontal axis for all range of the continuous axis. If we try to plot it, then this is how it looks like. It's analog, amplitude, continuous time. Right? Continuous time. Now, if we look at digital, continuous time, so it exists at continuous time, yeah, continuous time, but the amplitude is digitized. In this example is 1 and 0, for example, right? So, so the first part is digital, the amplitude, then is continuous time, then is when the signal exists. So here, same here, analog, referring to the amplitude, it can be of continuous range. Analog, discrete time, so it exists at discrete time. And then we have digital, discrete time, so digital amplitude, and also at discrete time. Okay, I hope you're clear about these four basic classes of signals, which are very important. Okay, periodic and aperiodic signals. A signal ft is said to be periodic if it repeats itself at a regular interval. So T naught is what we call the fundamental period of the signal ft. It is the smallest period that satisfies the periodicity condition. So T naught is the fundamental period. It is the smallest value of the period that satisfies the periodicity condition. A periodic signal remains unchanged when time shifted of integer multiples of the period. Okay, this is an example of periodic signals. Okay, it repeats itself at regular intervals. When it's time shifted by integer multiples, it remains in the same shape. Okay, a signal that is not periodic is said to be aperiodic. Causal and non-causal signals. Okay, causal signals are signals that are zero for all negative time. Okay, the amplitude are zero for all negative time. Okay, this is causal signal, right? Okay, if we have this one, oh, I should change the color. Sorry, so this one, this is causal signal. Signals that exist or have amplitudes, okay, exist lah. The right term is exist. The signals exist for t bigger than 0, and it is equivalent to 0 for t less than 0. Okay, anti-causal signals are signals that are 0 for all positive time. Okay, that means for t bigger or equal to 0 is 0. So it only exists at the negative time. Okay, that is anti-causal. This is anti-causal signals. And non-causal signals are signals that have non-zero values, okay, in both positive and negative time. So this is non-causal signals. So in this course, we deal with causal signals. Okay, causal signals means signals that exist from t equivalent for t equal to 0 and positive t. Yeah, that means on the right hand side of the time axis here on this. Okay, for t less than 0 is 0. So that's causal signal. And in this course, again, I'm emphasizing we deal with causal signals. Okay. Even signals and odd signals. A function or a signal is even if xt is equals to x of the negative of t. This is how it looks, an example of it. So if we have a signal okay, xt, and then we try to sketch the x of negative t, and we find that the x of negative t is the same as xt, then we call it, okay, an even function. Okay, if you try to plot for this diagram, this is xt. So if you try to plot x minus t, then you will get you find that it is the same as, it looks the same as this one. So this is an example of an even signals. An odd signal, okay, a function is odd if xt is equals to the minus of x negative t, okay, or the xt is equals to the negative of x of the negative of negative t, okay. So an example is this. So we have this signal xt. So if we try to plot x negative t and then taking the negative of it, then you'll find that if it's the same as xt, then that function or that signal is an odd signal, right? Okay, for all signals, okay, we can separate the signal to the odd and the even component. In other words, a signal ft, it is equivalent to even signal plus the odd signal, where the even part is given by taking 1 over 2 of the addition of ft and f minus t, okay? And the odd function, or sorry, the odd component of a signal is given by taking the 1 over 2 of ft minus f minus t, okay? So we need to say that whatever signals that we have, we can separate the odd and even functions. Or in other words, all signals are composed of all signals are composed of the even and the odd component, where the even component of the signal is given by this equation and the odd component of the signal is given by this equation. So when we want to find the odd component or the even component, can you tell what you need to know? You need to know, okay, of course, this ft, the signal itself, okay, you need to know ft, and then you need to know what is f negative t. Okay, so if you add ft and f negative t and you take 1 over 2 of that signal, you divide that signal into you divide the addition into 2, that would be the even component of that signal. On the other hand, if you take ft and then you minus it with f negative t and then you divide it into 2, that would be the odd component of the signal. Okay, you can check. Okay, when if you take the fe and f naught, the even component and the odd component, you add these two equation, you get ft, right? Okay. Even and odd components, they have basic properties, and it is equivalent to the mathematical formulation. If you have even function or even signals, you multiply it with an odd function or odd signals, then you get an odd function. If you have an odd function, you multiply it with an odd function, you get an even function. And if you have an even function, multiply it with an even function, you get an even function. So I will upload some videos on this topic. So please watch for further understanding. A signal whose physical description is known completely are known as deterministic signals. Each value of the signal is fixed and can be determined by a mathematical expression, rule, or table. The future values of the signal can also be calculated from past values with complete confidence. There's no uncertainty about the values. Okay, so signals or functions with mathematical expression, they are all deterministic signals. Probabilistic or random signals, the amplitude values cannot be predicted precisely but are known only in terms of probabilistic descriptors. These are signals which are we estimation based on not estimation but signals which are estimated, yeah, based on probabilistic functions. Okay, so if we have a probability functions, okay, we can consider them as signals also, yeah. Okay, the future values of a random signal cannot be accurately predicted and can usually only be guessed based on the averages of sets of signals. Okay, there's a process which is called stochastic process, which is used to evaluate or model probabilistic or random signals. Finite and infinite length signals. This is quite straightforward. A finite length signal is non-zero over a finite set of values of the time. Okay, an infinite length signal is non-zero over an infinite set of values of the time. An example is the sinusoid. How do we measure signals? How do we determine the size of signals? So one way of determining the size of signals is by finding the energy of the signal. So for real signals ft, the energy is given by taking the integration from minus infinity towards infinity of the square of the signal. If you look at this expression, it is actually the area under the graph, isn't it? So we can measure the size of a signal by finding the energy of the signal. But if the signal has amplitudes which goes towards infinity as time goes to infinity, we cannot find the area under the graph, isn't it? So for this kind of signals, okay, we cannot use this formula, or we cannot use the energy as a measurement of the size. Okay, so I repeat, we can measure the size of the signals by finding the energy of the signals if the signal has amplitudes which approaches zero as time goes to infinity. Okay, because the formula or the expression for energy is given by this, where it is actually finding the area under the graph, right? So for those signals which signals which have amplitudes that approaches infinity as time goes to infinity, we find the average of the square of the signal amplitude, or the mean squared value of ft, which is actually the power of the signal. Okay, so we use the formula, or we find the power of the signal as a measurement of the size if the signal has amplitude which goes to infinity as time goes to infinity. Okay, so we come to the last class of signals, which are the energy and power signals. Okay, based on what I've discussed from the previous slide. Okay, so if we have a signal, okay, so if we measure the signal and we find that we can find the value for energy, okay, then that signal is considered as an energy signal. Okay, so a signal with finite energy is an energy signal. What this means is that the necessary condition for a signal to be of energy type is that the amplitude goes to zero as time goes to infinity, like I've discussed in previously. Okay, so if we cannot measure the energy, right? So we find that the energy is infinite, right? So we measure it using the power formula. So we try to find the power, right? So a signal with finite and non-zero power is a power signal. So that means we measure it using the energy formula. We find that the energy is infinity, okay, or we find that then we apply the power formula and we find that it has finite and non-zero power, so that signal is considered as a power signal. Okay, so if the signal is a power signal, that means we are able to find the mean of the signal or the entity. Okay, which is we are able to average it over an infinite interval. So that means this signal is periodic. Okay, okay, can you imagine that? Or it has some statistical regularity, because we are able to find the average over an infinite interval. Okay, think about this, yeah. So a power signal has infinite energy. That's true, right? So if we apply the energy formula and we find that the energy is infinite, so that means we can apply the power formula. So then it becomes a power signal. That means a power signal has infinite energy, and an energy signal has zero power, right? Okay. So what this means is that a signal can either be a power or an energy signal. It cannot be both. However, there exist signals that are neither power nor energy. Okay, a signal cannot be both power and energy signals, uh, 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 but the signal can be neither power nor energy signals, such as the ramp function. You can try, okay, the ramp function. Yeah, so it is impossible to generate a true power signal in practice. Okay, because in practice, in real life, such signals, okay, would be a signal which has infinite duration and infinite energy, right? So, okay, because true power signals, I mean, the signal is infinite energy, right? Okay. So the next point is because of periodic repetition, periodic signals, which are the area under f squared, okay, over one period is finite power signal. Okay, because of this periodic repetition, okay, periodic signals, they are power signals. But not all power signals are periodic. Okay, so periodic signals, they are power signals, but not all power signals are periodic. Right? So that is chapter 1. Please view the videos and look at the examples. And I'll see you in the next video for the next chapter.